Hello again. This is Math 2231 coming to you from the College of DuPage. And the title of this lecture is Rectilinear Motion Redux, LSA 12 Reflections. As always, please be an attentive listener while watching this video. The problem again dealt with rectilinear motion, and the graph below shows the velocity of a particle measured in feet per minute along the x-axis. Use the graph to answer the following questions, and please include the correct units. And so you're supposed to answer the questions and explain your answers completely. What is the velocity and acceleration at time t equal 1 minute? Number 2. Assuming the particle began its journey at 10:13 a.m. exactly at the origin, at what times did the particle change direction? Your answers should be exact, including seconds if appropriate. Number 3, assuming again the particle starts at the origin, give the location of the particle at time t equal 10 minutes. Number 4, what is the average velocity and average acceleration for the particle during the interval from 0 to 10 minutes. And last but not least, number 5, at what times is the particle furthest from the origin? And although I didn't ask it, I could have asked you how far is it from the origin as well. Okay, let's dive in and realize that here this is the velocity versus time, and so this axis has velocity in it. Okay, well, the velocity comes straight from the graph because it is a velocity graph. And so you see at time 1 minute, you are at 15 feet per minute because this is just the velocity graph. Now, acceleration is the change in velocity, so acceleration equals the slope of the segment that connects 0, 0, and 230. And that is going to be the slope there. It goes across 2 minutes, and it changes 30, so it is also 15, but the units are different. It is 15 feet per minute squared. Now, you change direction when the velocity changes from positive to negative. So the particle is going in a positive direction here, here, and here, but then it starts going in a negative direction after you cross this. So it changes direction twice, here and here. And so it changes direction when the graph passes through the x-axis. And remember, we started at 10:13. And you see, this point is 4:30. This point is 6 minus 30. So 2 points determine a line. So this is v minus the v coordinate is equal to the slope. The slope of that is minus 30 times x minus 4. And for those two things to be, well, first of all, when you hit the axis here, when you're changing direction, the velocity going from positive to negative, v is 0. And so we put 0 there and we solve and we get 5. Now, if you add 5 to 10:13, you get 10:18 exactly. Now, the other one was a little bit harder because we're going from this point, which is 9 minus 20, to this point that is 10:10. And so that is a different line. It is v minus 10 is equal to 30 times x minus 10, the whole of x minus 10. And you set v equal to 0, and you solve this, and what you will get is 9 and 2/3, and 2/3 of a minute is 40 seconds, and if you add 9 to 10:13, you have 10:22. So that's why you have those answers. So those are the answers for A and B. Number C, you realize that since distance is equal to rate times time, distance is the area under the velocity and time curve. And you see you can slice these things up, and you can find that this area is a triangle, and that is going to be an area of 30. This area is 60, and that is 15. Now this is all while you're going in a positive direction, but then you turn and go the other direction. And so these areas can be thought of as being negative since you're going in the other way. And so again, here you go 90 and 15 is 105. So you go from 0 to 105, then you turn around and you start going negative, and you get these. We're slicing this into little pieces. and we get this, and here's another positive piece. So you take this number and combine it with that number, and you subtract off that number, and that tells you that the answer to all of that is a positive 20. And so that's where you end up, a positive 20 to the right of the origin. Now the average velocity is the change in velocity. So you see the beginning velocity was what was here, and you well, average velocity is change in distance over change in time. You change from 0 to 20, so, and you divide by 10 minutes, so it's 2 feet per minute. That's the average velocity. And the average acceleration is the change in velocity over the, and you see the velocity. Now remember, this is a velocity curve, and so the velocity changed from 0 to 10 in 10 minutes. So it's 1 foot per minute squared. And you were furthest from the origin when you were here, because that was 105, and that was at time t equal 5 minutes. Now, the reason I wanted to do this problem now is that we're moving into talking about integration, and the physical interpretation of integrals is area, in quotes. So there are some key takeaways for students to have. One is that area has physical significance. You saw that in this rectilinear example. It is important for students to realize that rectilinear motion involves both derivatives and integrals. It's important for students to realize that areas can be calculated via geometric slicing, and we're going to be doing that very soon in a technique that we call the Riemann sums. And of course, since this is calculus, we're going to be using limits as well. And another important thing is that in air quotes, areas can be positive or negative if you think about the context correctly. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care, because self-care is important. And take care of each other as well, because we're all in this together. Look forward to seeing you in class. God bless you all.